The wiki, the rise, fall, and rebirth of in-circuit emulation part 1 of 2. Key takeaways. The exponential growth of semiconductor innovation has led to a large and more complex system on chip SoCs, posing significant challenges in design verification. In-circuit emulation marked a pivotal shift in verification, enabling design to be tested at much higher speeds and with real-world conditions compared to the traditional HDR simulation. Modern speed adapters have evolved to enhance debug capability, incorporate real physical layers to accuracy testing, and support multi-user deployment, solidifying the role in mainstream system validation. The introduction. The historical roots of hardware-assisted verification. The relentless pace of semiconductor innovation continues to follow the unstoppable trend, the exponential growth of transistor density within a given silicon area. The abundance of available semiconductor fabric has fueled the creativity of design teams, enabling exponentially advanced system on chip. Yet the value scale that empowers new possibility also imposes several challenges on the design verification. As a chip grows larger and more complex, the test environment required to validate them expanded proportionally in both scope and certification. These test workloads demand longer execution times to achieve meaningful coverage. The combination of ballooning the design sizes and heavier test workloads push the traditional hardware description language HDR simulation environment beyond their limits. In many cases, simulators were forced to swap designs in and out of the hosted memory, creating bottleneck that drastically slowed execution and reduced verification throughput. Back in the earlier 1980s, a few pioneer startups sought alternatives beyond the simulation engine. JTAG was among the first to experiment with dedicated hardware-assisted verification engines. While innovative, these early tools were limited in flexibility and had short lifespans. The breakthrough came short, thereafter with the rise of a configurable platform built around the field programmable gate array BGAs. By the mid 1980s, the two trailblazing companies, ICOS Systems and QuickTime Design Systems, began developing the first generation of hardware-assisted verification HAV tools, including the hardware emulators and FPGA-based prototypes. And though initially the emulation platforms were large, heavy, unreliable, and expensive to acquire and operate, they introduced a new paradigm in design verification by enabling orders of magnitude speed compared to simulation alone. Early deployment mode in circuit emulation. The early adoption of hardware accelerated in the design verification process marked a pivotal shift in how semiconductor designs were tested and validated. The initial deployment mode for HAV was in-circuit emulation. This approach offered two key breakthroughs. First, the hardware-based verification engine enabled the execution of DUT, design under test at speed several orders of magnitude faster than a traditional HDR simulation environment. Whereas the HDR simulator typically operated and still operated frequencies in tens of hundreds of hertz. The hardware-assisted platform could run at megahertz level speeds, enabling verification of much larger and larger complex design with practical time frames. Second, in-circuit mode made it possible to drive DUT with real-world traffic, rather than relying solely on artificial stimulus such as software-based test benches or manually crafted test vectors. By connecting the emulator directly into the socket of the actual target system, It could validate the behavior of the design under realistic operating conditions. That this not only improved the thoroughness of functional verification, vastly more testing could be executed in the same time frame, but also its accuracy because of the fidelity of the real-world test bed not achievable with the virtual test bench. Thoroughness and accuracy contribute to reducing the risk of taping out a faulty design and avoided massive impact on the financial bottom line. The devil in the clock domain need for speed adapters. From the outset, a fundamental challenge in ICE deployment becomes apparent. An inherent clock speed mismatch between the target system and the duty hosted with the HAV platform. Target systems such as a processor board, IO prefers, and a custom development environment operate at full speed production speed, typically ranging from the hundreds of megahertz to several gigahertz. In contrast, the emulated duty runs at a much lower frequencies, often only a few megahertz, constrained by the intrinsic limitation of hardware emulation platforms. This vast time disparity, often spanning 3 or more orders of magnitude, makes cycle-accurate interaction possible, resulting in potential data loss, synchronization issues, and non-functional behavior. To address this, speed adapters were introduced as an intermediary layer, conceptually implemented using the FIFO buffer. These hardware components were inserted between the emulator I/O and the target system to decouple the asynchronous high-speed nature of the real world from the deterministic slow execution of the duty. The early implementation of speed adapter, 1985 to 1995. ICE promised dramatic improvement in verification productivity in virtue of high performance and accurate test workload. However, the need for speed adapters introduced challenges of their own in flexibility, scalability, reusability, and single-user debugging efficiency, remote access, and reliability. Lack of flexibility. Speed adapters are protocol-specific hardware implementation, each designed to support a particular interface standard, such as PCIe, USB, or Ethernet. This made them inflexible or non-generic. Implementing a new adapter for different protocols often required custom engineering work, from a development and a precise synchronization logic, and even small variation of protocol version of a signal timing could lead to incompatibilities. As a result, the setup process becomes complex and error-prone and time-consuming. Limited reusability. Each speed adapter was essentially a one-off solution tailored for a specific interface and usage scenario. Reusing adapter across project, even though this similar hardware often proved impractical due to the slightly architecture of timing difference, and furthermore, since these adapters were fixed function hardware, they did not allow for corner case testing, protocol tweaking, or exploratory what-if analysis. This led to hampered their usefulness in iterative or exploratory verification workflow. Frustrating and error-prone design debug. One of the most serious drawbacks of ICE mode was difficulty of the DUT debugging. When the target then drove the design under test, the behavior of the design under verification become non-deterministic. A bug might appear in one run and vanish in the next, making root cause analysis extremely difficult. This lack of repeatability stemmed from the asynchronous, event-driven nature of the interaction between the real system and the slower emulator. Without a deterministic control over the inputs and timing, capturing the tracing their failure becomes a frustrating and prolonged process. Cumbersome remote access. In increasing the distribution engineering environment, remote accessibility become a key requirement. Ice mode, however, suffered from a fundamental limitation. It requires physical access to plug and unplug the target system in from the emulator. Without someone on site, remote team were effectively blocked from initiating or modifying the test scenarios and creating a bottleneck for a gradually distributed development team and undermining this continuous integration workflows, ripe risk and maintenance overhead. Like any hardware, speed adapters had a finite mean time between the failure MTBF. A malfunctions adapter might introduce intermittent and misleading behavior, leading verification engineers to chase the phantom bugs in DUT when those issues set in the speed adapter hardware. This could significantly delay the debug cycles and erode confidence in the verification platform. As a preventative measure, regular maintenance and validation of the testers were required, adding operational overhead and further complicating the test setup. The virtual takeover, the shift from ICE to virtual verification, 1995 to 2015. Within just a few years, the limitation of the first wave of speed adapters became apparently the rigid and simplicity of their design limited the deployment scope to manage data traffic between the time domain, the inability to handle flow control, packet integrated full system, in synchronization is created a significant bottleneck that could not scale with the growing complexity of SOCs. As a result, the industry shifted its focus toward a more sustainable approach, virtualization. ICE gradually lost its appeal and ceased to be in the default method to the forced system verification. It was pushed to the final stage of validation, used mainly for full system testing with real-world traffic just before tape-out. Meanwhile, a promising approach emerged in the form of the transaction-based emulation, often referred to as virtual ISO or transaction-level modeling (TLM), instead of driving the DUT with physical target systems via physical speed adapters. This method used software virtual interfaces like digital twins and physical speed adapters drive and monitor the DUV through the high-level abstraction. The shift from bit signals accurate physical emulation to protocol accurate virtual emulation marked a critical turning point in the evolution of HAV platforms. It enabled a new class of verification use models that were more flexible and expansive in application and better aligned with modern SoC design methodologies. The advantages of this shift were numerous and transformative. Higher performance by replacing cycle-accurate pin-level I/O with abstracted transactions, the emulator could operate at significantly higher effective speed, enabling faster verification cycles. Greater debug visibility. With all communication occurring in the digital domain in sync with the emulator, the test environment becomes deterministic, making it easier to log, trace, and debug data flows without intrusive proofs in external logic analyzer. Simplified setup. The virtual platform eliminated the need for complex scaling, cabling, custom sockets, or fragile speed adapters, making emulation setups more robust and scalable. Remote accessibility. Engineers could now do emulations from anywhere via remote access to the most workful host workstation, making collaboration easier across geographies. Software co-verification, perhaps most importantly, transaction-based emulation enabled tight integration with embedded software development. Developers could boot operating systems, learn production firmware, and validate complete software stack alongside hardware long before first silicon became available. Collectively, these breakthroughs elevated the HAV platform from a specialized tool to an indispensable cornerstone of the verification toolbox, By the late of 2000s, no surgery development could achieve the predictable schedules and quality without leveraging virtualization verification methodologies. Third generation of speed adapters, 2015 to present. Over the past decade, the EDA industry, recognizing the unique testing capability of the ICE, revisited technology and committed significant effort to overcoming the shortcomings of the earlier generation of speed adapters. The focus shifted toward mitigating the critical bottlenecks that had long constrained flexibility, scalability, debugging accuracy, and system fidelity. The third generation of speed adapters were introduced greater configurability, smarter buffering techniques, and a range of advanced mechanisms designed to bridge the gap between the functional verification and true system-level validation. This enhancement paved the way for broader adoption of the in-circuit ICE in the verification, increasing the complex SoCs. Major enhancement of third generation SA speed adapter. Enhanced debugging, enhanced design debug. Modern speed adapters have significantly enhanced debug capability in ICE environment. Protocol analyzer and monitors are now instantiated inside the adapter in both high-speed and low-speed both-sided adapter, enabling bidirectional traffic observation. By correlating activity across these interfaces, the system provides a protocol-aware, non-intrusive high-level debug environment that was previously unattainable in ICE. See Figure 1. The Figure 1 state-of-the-art speed adapter solution through synopsis. This approach mirrors what has long been available in virtual platform. In virtual platforms, whether the handling Ethernet package or the PCIe transactors include the C-based monitoring coded in that aspect of the traffic. The results are displayed in the protocol-aware viewer, allowing engineers to analyze packet-level activity directly, similar to what an Ethernet packet sniffer would provide, without resorting to low-level waveform dumps. The result improved debugging efficiency and faster root cause analysis and hardware-assisted verification. The verification via real-file and interoperability. On modern flipper interface, whether the PCI Express, USB, Ethernet, CLX, or others are built on the two fundamentally blocks the control and the physical layers. The controller is a purely digital block that implemented the logic of the communication product, encoding a packet handling, flow control, and error detection. The PHY is mixed signal design, bridging the digital and analog world. It manages the voltage level, current drive independence, timing margin, and the electrical signals that allows data to move across pins, connectors, and transmission line. In transaction levels flow, the PHY cannot accurately presented. To work around this limitation, the PHY is substituted by a simplifying or fake model that allows basic register programming but omit the critical analog behavior that dominate the real-world operations. Such models cannot uncover issues that manifest only the physical interface. To overcome these blind spots, modern speed adapters integrate real files into the hardware-assisted verification flow. By introducing the genuine physical interface into the loop, design teams can validate their duty against their real-world conditions rather than the abstracted models. This capability brings several tangible benefits. Accurate link to training and initialization. Protocol like PCIe, CLX, and USB require precise electrical handshake to establish communication. This can be only exercised with the real PHY. Timing and signal integrity validation. Engineers can detect marginal failure, jitter, or power-related issues invisible to fake models. Protocol compliance and the electrical layer ensures interoperability with other vendors' devices and adherence to industry standards. Higher silicon confidence. By testing against true physical interfaces, teams dramatically reduce the risk of surprises in silicon bring-up. Today's design teams are confronted with two very different, yet equally critical and challenges. On one hand, they must continue to validate to support legacy interfaces that remains essential in many deployment systems. In these cases, speed adapters can integrate FPGA that implementing legacy file, enabling seamless connection to the external environment and ensuring the backward compatibility with the established standard. On the other hand, the teams are also working on advanced next-generation protocols that are still in the process of being defined and redefined. For these emerging standard speed adapters incorporate real PHY IP test chips, providing direct access to the world's analog behavior that virtual models cannot capture. Companies like Synopsys with expertise in both PHY IP and hardware-assisted verification are at the forefront at this shift. Their solution allowed design teams to test interoperability earlier, accelerate development cycles, and bring new products to market with far greater confidence. The system validation servers. For protocols such as PCIe, relying on a standard host server tested environment is not feasible. This limitation stems from the server's BIOS, which enforces strict timing settings. These times are easily exceeded by relatively long responses times of an emulation system. Once triggered, timeout causes the validation process to stall or hang, preventing the meaningful progress. To achieve a complete ISA, this challenge must be addressed head-on. The answer lies in the purpose-built system validation server equipped with a modified BIOS. By removing or adjusting the restrictive timer parameters, the server can operate seamlessly through responses of the emulated design. So system validation server in-circuit emulation. This is out-of-the-box solution offers immediate practical benefit instead of spending months back and forth iteration with an IP department to obtain the configure a host machine with a customized BIOS. Validation teams can deploy the ready-made a server that works from any one. The result is dramatically reduced in setup overhead, faster time to validate, and more reliable environment for exercising the advanced protocol like PCI under real-world conditions. The ultra-high bandwidth communication channel. One of the most transformative advances in modern speed adapter is introduction of the ultra-high bandwidth communication channels between the emulator and the adapter. Today's leading-edge solutions can sustain throughput levels of up to 100 gigabps, enabling them to increase in the overall validation throughput. By approaching the communication rates of the real silicon, speed adapters allow the engineers to stress test SoCs under real workload, validate protocol compliance in the line rate, and observe the system behavior under continuous heavy traffic conditions. Moreover, this capability ensures the network-intensive applications such as those found in data centers, 5G infrastructure, and high-performance computing systems can be tested in environments that closely mimic deployment scenarios. The result is a dramatic increase in confidence that design will not only function, that also performed dramatically once in the field. Multi-user deployment. A single speed adapter can be logically partitioned to support concurrent multi-user operation. The adapter's resources can allocate their entirety to a single user or subdivided into up to 3 independent partitions each assigned to the different user. For instance, a 12-port Ethernet speed adapter may be configured a monolithic resources or 12 ports mapped to on one user or segmented into 3 logical groups of 4 ports each, enabling 3 users to access a discrete subset of the adapter in the parallel. The same partitioning capability applied to a PCIe interface. The adapter can expose up to 3 independent PCI links, each link operated in isolation and assigned to separate users. This features resources partitioning, port multiplexing, and independent link allocation are natively supported in the architecture of the speed adapter. Advanced buffering and flow control techniques. This architectural refinement eliminated the peaked drops and ensured deterministic behavior across the fast and slow clock domains. They also slowed the speed adapter scale with a large verification workload. Conclusion. Today's speed adapters combine a flexible and multi-user deployment and a stable and exceptional fast high-speed links, determined flow control and improved DUT debuggability, proven resilience under continuous data center workload. With these advanced third-generation speed adapters move the IC from the niche verification mode into mainstream, indispensably tools for system validation. Today's emulation platform, configured with third generation of speed adapters, finally bridges the gap between the functional verification, which validates DUT functionality, and I/O protocols, and system-level validation, which ensures the design interacts correctly with the physical world, and the holistic approach closes a long-standing blind spot in hardware-assisted verification, enabling faster debug cycling, higher quality silicon, and first pass success in increasingly complex SoCs. Okay. Thank you for your time. See you next time.